Okay, so we're going to look at this stress-strain graph and how we're going to calculate Young's modulus from this. So along the bottom of this graph here we've got extension, X, and up the side here we've got force, F. Now these are all related by these three formula. Stress is equal to force over cross-sectional area. Strain is equal to extension over original length, and Young's modulus, what we're after, is equal to stress over strain. So we've got the force, we can read that from the side of the graph. We've got extension, we can read that from the x-axis of the graph. Area we can calculate because we know the cross-section of the material was 10 mil, I'll put it in meters though, by 3 mil. Oops. And you can calculate area from that. Should be quite a small number. The original length was 200 mil, 0.2 of a metre. So as long as we get the force and area, we can use those to work out stress and strain, and stress divided by strain will give us Young's modulus. Now we can only do this on the straight part of the graph, so anywhere from here to here. Obviously don't pick points too close to zero because that's going to give you more errors, and don't pick points too close to where it goes curved because you risk it being curved. So for me, I'm just going to use a point here at 600, and I'm going to go down. Best if you use a ruler, and say that's 0.00012. That's where my point is there. And that's in meters, and 600 newtons. So I can do my calculations. So stress is equal to force, 600, divided by area, which in this case is 0.01 times 0.003, and that will give me, it gives me 20 million, so 20 times 10 to the 6 newtons per metre squared. That's my stress at that level. So quite a lot of stress. Strain is going to be equal to the extension. In this case that's right off the graph, so 0.000 3 zeros 1 2 roughly, divided by 0.2. This should be a very small number. 600 times 10 to the minus 6. No units because it's strain, so it's a small number. Now Young's modulus is going to be equal to our 20 times 10 to the 6 divided by 600 times 10 to the minus 6. Now if I type that in, if we're dividing a big number by a really small number, i.e. a number smaller than 1, we should get an even bigger number, and we do. We get a number that is 33.33 times 10 to the 9 newtons per metre squared. So that's 33 giganewtons per metre squared, or 33 gigapascals. What we need to do is verify whether that's correct. So for polypropylene, if you go onto something like Engineering Toolbox, type in Young's modulus for polypropylene, find out what it is. I believe it's somewhere in the region of 30 to 35 giganewtons per metre squared. So this result here, 33 giganewtons per metre squared, is quite realistic for that. Now obviously you can choose different values of force. I'll do it in a different colour. Maybe you could choose it here at 400 or something and go down. It should still give you exactly the same value of Young's modulus because it's a straight line. even though you're putting less force on, it's stretching less, and the calc should come out the same, exactly the same. What you also need to talk about in your assignment is your chances of getting things wrong here, errors. So, for example, with my red line here, I came down and I estimated it's at 0.00012, but it could be 0.0013. The thickness of my line might be out, my line might be to slant. There is that possibility of error there. So you do need to talk about that and have an awareness that this might not be exact and you might be incorrect in what you're doing here. So put this, if you calculate it like I've done here on the paper, scan that, put it in your document, put a description of how you did the test, and put a little bit afterwards about does this actually match up with what you would expect for polypropylene, and talk about any ways that errors could come into your assignment.